So if I isolate our link here, we're applying, again, this value of P on top, this value of P on the bottom. And for the Euler buckling, we're only looking at cases where we only have an internal normal force. We don't have a shear or a bending moment or anything like that. And these are being applied through the centroid, are always going to be the assumptions we have to make to use these equations. So we want to align this in the proper dimensions with how it's being applied in this situation. Right, so the nominal length is 24 inches. We're going to be 1.5 inches in this direction. And 0.5 inches along that dimension. They don't give us a coordinate system, so I'll establish one here. I'm going to call this the x direction, the y direction, and the z. So based on the picture, if we look at the left side, it's pinned along that direction. But if we look at the other side, it's fixed. And this is going to affect the effective length depending on if we're looking buckling around the x-axis or buckling around the y-axis here. So based on how this picture is, along which axis does the pin go through, the x-axis or the y-axis? The pin is going through along the y-axis. So just for our diagram, this is our pin. So when it's bending around the y, it's going to be a pin-pin direction. It is allowed to freely rotate around the y-axis. That's what makes it a pin at the top, a pin at the bottom. But around the x-axis, that pin is preventing rotation around the x-axis there. So that gives us a different type of connection when we're going to be looking at the buckling around the x-axis. So pin parallel to the y, so it's parallel to the shorter dimension in this case. So what we want to look at is we have to look at how much does it take to buckle around x, how much does it take to buckle around y. We also have to consider, is it going to buckle at all, or is it just going to crush, and see which one happens first. Or at least test our buckling, the stress when we buckle versus the stress it would take to crush it. Okay, so I'll start to see what is the load it would take for it to buckle around that x-axis. Okay, so the first thing is when I go to use the Euler formula, the pi squared EI over KL squared, I need specifically the I around the axis that I'm testing the buckling. Again, for it to buckle around x, really what it's doing is it is bending with respect to that x-axis there as we start to crush it down. So we need to know what is the Ixx, so what is the area moment of inertia around the x-axis. So in this case, x, the x-axis, is the neutral axis that we're looking at for this segment. So in this case, we're going to be squaring the 0.5 inch term. I'm sorry, cubing the 0.5 inch term times 1.5 inches over 12. So around the x-axis, it has an area moment of inertia of 0.0156 inches to the fourth. And that will be different because it's not symmetric. It will be different than what it takes to bend it around the y-axis. I'll call that coefficient here for the effective length kx since we're bending around the x-axis. Again, this depends on what the end conditions are with respect to bending about this axis. So if we're trying to bend around x, with respect to the top and the bottom, it's fixed. It does not allow free rotation around that x-axis as it starts to bend. So in this case, because it's fixed at the top, fixed at the bottom, we have fixed ends, which in this picture is c. So that k value is 0.5. Effectively, it halves the length of our column. So we have the k value, we have the I value. Those are what are going to change between the two axes that we're considering. So we want to see what does it take, what load would it take to buckle around the x-axis. So now we can use our formula for our critical load. So P critical, I'll call this around the x-axis, is pi squared times the Young's modulus for our material, 29 MSI, megapounds per square inch, times the area moment of inertia around the x-axis, divided by the effective length squared. Again, the effective length is this k value times our nominal length, and that quantity is squared. It's not just L, it's k times L that gets squared. We calculate all of this out. The critical load for it to buckle around the x-axis, it would take 31.1 kip for it to buckle around that axis. But again, potentially it could buckle around also the y-axis, especially because it's pinned there. So in this case, it's a little tough to see. If it were to buckle this way, this is going to bow out around the x-axis, either along this direction or along this direction. And that's how it's going to fail in that mode of buckling. What we also would consider is, what if it buckled around the y-axis? So it actually bows out this way or bows out that way. And in this case, the top and the bottom are free to rotate around that pin connection for it to fail. Right, so also we want to check then, what does it take around the y-axis? For our area moment of inertia with respect to the y-axis, now the y-axis is our neutral axis. Right, so that's going this way. So now perpendicular to this axis is the 1.5. That's going to get cubed times 0.5 over 12. So as we should expect, it's harder to bend it in general around this axis. The area moment of inertia is higher here, much higher, about 10 times as high. So 0.141 inches to the fourth power. Again, remember, loose definition of area moment of inertia describes how difficult it is to bend around that axis. But there's more to it than that because of these end conditions. In this case, our k value around the y-axis, because it's a pin-pin connection around the y-axis, we have picture A here, we have a pin-pin end. Our k value increases or doubles to 1 for this condition. So now we want to consider, what load would it take to buckle it around the y-axis. So P critical around y. Again, the I value changed. It's now much larger. And the k value is now 1 times our nominal length of 24, and that is going to get squared. So the amount of force it's going to take to buckle it around the y-axis is going to be 70 kip. So we have to consider, again, like we have in the past, if we have multiple ways something can fail, we have to consider which one happens first. Because once it starts to fail in the first way, then all of our assumptions are kind of out the window, and then this is not going to happen. So we can't actually apply 70 kips to this and expect it to buckle around y, because it will have already started to buckle around x. So in this case, that is not going to happen. It's going to buckle around x first at 31.1 kip. If it were to buckle, it'll buckle around x before it would buckle around y, but that's not necessarily the same thing as saying it is going to buckle. That's the next test that we have to run. But first on this, any questions on calculating the two different critical loads of how it can fail due to buckling? Right, so we ruled this one out because it's too high. It would buckle around x first. So what we want to test is this actually going to buckle, or is it going to crush? So we can calculate, I'll call it the critical stress here. What is the stress in the column if we were to apply that buckling load that we would say buckles at the 31.1 kip? So in this case, we want to use that critical load we found, 31.1 pounds, or 31.1 thousand pounds, over the cross-sectional area, because this is how we compute our axial stress as we have in the past. Cross-sectional area, 1.5 inches times 0.5 inches. And we can see that the critical stress is 41.5 KSI. So at the point where we think it would just start to buckle around the x-axis, the stress in the material is 41.5 KSI. So with this analysis, is this indeed going to fail due to buckling, or is this going to fail due to crushing?
Buckling.
Right, so you have fail due to buckling. If we look at the yield stress, it's going to, and that's a compressive stress, because we're in compression here. The stress in the material is only 41.5 KSI. We are below the yield stress for that material. So it would not fail due to yielding. It is going to indeed fail due to buckling at the 31.1 kip. Right, so we've ruled out that it would crush before it would buckle. We've ruled out that it would buckle around Y. We know that the first mode of failure, at least that we're considering, is buckling around the x-axis. Now we can answer the last part of the question. We want to know what's the largest external force P that we can apply that we're still guarding against buckling with a factor of safety of 1.75. So remember, the factor of safety is the ratio of when our thing actually will fail, either due to yielding, or in this case where it would just begin to buckle, over the amount of load we're going to design it to handle. And we're saying we want a factor of safety of 1.75. So again, it actually fails if we have 31.1 kip. Which means we're going to design it, or recommend that we put at most an external load of our design load, I'll call it PD or P design, at most 17.7 kip.